Thank you. Let me show the title at the beginning again. You can reach our this webinar and previous webinars in our YouTube channels as well. So we are recording this webinar as well. So, like I said, I want to start with making a small introduction about our Wisdom Forum. Wisdom aims to provide a platform to support and empower and encourage the participation of all genders in OR within the Euro community. What we're trying to do is we basically try to advise or highlight best practices to the Euro executives on issues that women face in the, especially in the operations research community. We try to promote championing, networking, and mentoring, particularly of women at the early stages of their career in OR. And actually, Young Women for OR initiative is a part of this goal. We'd like to promote a conversation around how OR can be utilized to help create a diverse and inclusive future. And you can find our EDI policy on the Euro website. If we come more specifically to the Young Women for OR initiative, like I said, this is one of our goals, and this initiative aims to highlight early career young women working in OR, either in academia or in industry. What we do is we promote the selected individuals by spotlighting their work through Euro channels and by providing networking and mentoring opportunities. And each year we select 12 young women for OR. And this year we had 32 applications from 13 countries, and the awardees are here. Congratulations to all of them. This was announced in our winter event in December. And today we are very excited to have 3 of our Young Women for OR awardees presenting their work on location and routing. Let me quickly go over their names and their titles. So first, we're going to have Afaf Aloullal presenting multi-period single-allocation hub location and routing problem. Then we're going to have Bakker presenting pattern recognition meets branch and bound regional branch variable selection for the capacitated facility location problem. And then we have Paula Segura Martínez solving the rural postman problem with a fleet of drones. And we're very happy to have our subject matter expert, Professor Sibel Alumur Alev. Professor Alev is an associate professor at the University of Waterloo. She has a PhD from Bilkent University and a postdoc researcher. She served as a postdoc researcher at the Karlsruhe Institute of Technology. She has a very impressive CV, including awards from Inform's Chuck Revel Rising Star Award. And her research interests are mainly in the in optimizing facility locations and logistics operations, and we are very grateful for having her here. So the way this is, the webinar is going to work is we're going to have 10 minutes for each of our young women for our awardee for their presentations, and then we are going to hand the stage over to Professor Alev. Okay, so Afaf, can you please share your screen?
Yes, of course.
Start your presentation. Thank you.
Can you see my screen? Yes. Yes. Okay, perfect. Hello, everyone. My name is Afaf Aloullal. I'm a PhD student at Polytechnic University Hautz-de-France. I'm very happy to be here with you and present my work titled on multi-period hub location routing problem. I'm under the supervision of Francisco Saldania de Gama and Radza Tudosiewicz. And my presentation, I'm going to start with a brief introduction. I'm going to present an example to understand a little bit the features that we are working on for this specific problem. And then I will omit the mathematical formulation just to focus on the solution approach, the approximative method that we propose for this specific problem. And then I will present the results along with the conclusions and the perspective. Let's start. So imagine, let's assume that there is a company that wants to build its network in France and to transport a product or several products all over the country. So, of course, this company needs to have a strategical planning. A strategical planning needs to cover multiple periods, because this kind of investments, opening hubs, building the network are huge investments that needs to be over time. We cannot invest these or build a whole network in 1 or 2 years, but in a several period of time. So these kind of projects, at each period of time, the company face several decisions. The first decision are how many hubs need to be open and where to locate them. Also, the interconnection between these hubs, and also the allocation of the nodes to each hub, and finally, the routing decisions. As you can see from this small example, my problem that we were studying is the multi-period single allocation hub location routing problem, while assuming one route for each hub and incomplete network design, since each hub need to be not forcefully interconnected with all the hubs. So we have incomplete inter-hub network. And also we assume that the hubs are capacitated. So as you can see, already the problem is combining two NP hard problem, the hub location and the routing problem, and while adding the multi-period and the capacity of hubs and the incomplete network design, it makes the problem harder and harder. So yeah, we had to think about an approximate method that we could solve the instances that a general solver could not solve. So before diving into our solution approach, let's understand what we expect from the multi-period setting. Of course, the multi-period setting, we're gonna decide over multiple periods. So we assuming that the demand and supply will be increasing over time, also, as well as the costs also. So having this in mind, we propose a backward procedure starting from the last period. Why? Because the last period is the most constrained period in time of capacity and so on, because the hubs capacity are fixed, but the demand could be increased as well as the supply, also for the cost. So if we handle the last capacity in terms of open hubs and so on, then the other periods will be easier. So yeah, this is the math heuristic. It is based on 4 phases, and also we divide the problem into 2 sections: the network design, where all the decisions are needs to be taken, unless the routing part, and also the routing part. So first we start, as you can see here, from the last period, and we have 4 phases. The first phase is the phase of promising hubs. Here we do LP relaxation to the whole problem over all the periods to find the promising hubs, a small set of the nodes that are very likely to be hubs. And then once these, of course, here we are using only the network design, because the routing part did not really matter in this phase or in this part of the solution. So here, once we detect these promising hubs, we start finding, the second phase is to find the feasible solution. From that set of promising hub, we try to open only one hub, then if it's infeasible, 2 hubs, then if it's infeasible, 3 hubs, and so on, until we find a feasible solution, using, of course, a general solver and with a time limit. Once we find a feasible solution, we go to the next step, which is improve solution phase. As you can see here, we're still in the last period of time. So in the improve phase, we improve solution phase, we use local branching constraint, we use variable neighborhood descent principles to improve our solution. Once we find the best solution that we could find for the last period using the network design, then we go to the last phase, which is the backward fix and relax. We fix the network design part, and then we solve the routing part for the last period, which is the fourth period. And then we go back to the period before. So here, as you can see, we find the last solution, the solution of the last period. And these sets, of course, we will use them to find the solutions of the other periods, the below periods. So for example, in the third period, we find only 2 hubs instead of 3. Because the demands are less and the supply are less and so on. So we solve the network design, and then we solve the routing and so on until we find a feasible solution for the whole problem. So for this example, we open 1 hub for the 2 periods of time, the first 2 periods of time, and the third period we open another hub, and for the fourth we open another hub, and like that we find the final solution of the whole problem using our math heuristic. So now let's see the results. So our math heuristic, we solve up to 50 nodes. For the small instances that could solve up to optimality using a general solver, the math heuristic finds 70% of optimal solutions, exact solution of the general solver, and only 0.04% in the gap for the other 30% instances. And the average time of the math heuristic using the small instances, the 10-node instances, were just 7 seconds. For the medium instances, like 20-node instances, the general solver, in our case, we used Cplex, could not find a feasible solution within 8 hours of time. And our math heuristic find better solution, and the gap between the Cplex solution and the math heuristic ranging from 3 up to 90%, which is a huge gap, and only with an average time of 6 minutes compared to 8 hours. And here we can see the CPU time increase with the instance. So we start by 7 seconds, and using 50 nodes instances, we consume 1 hour 30, which is a reasonable time, while seeing the high quality solution that we get from our math heuristic. One question that could be asked is the multi-period setting worth considering, because multi-period setting, of course, it makes the problem harder, which is already combination between 2 NP hard problem and so on. So we did a comparison between using a set of instances, using the single period and the multiple period. The single period, the network design do not change over time, but multi-period, of course, it changed, as we saw in the example of the math heuristic. And we find out that using the multi-period setting, we could save up to 3% of total costs in the average. And 3%, it's a huge investment. It's a huge saving, because these kind of total costs are very huge investments. Like 3% could mean millions and millions. So let's see the conclusion, or the main points that we saw in this presentation. So a 4-phase math heuristic based on principle of relax and fix, variable neighborhood descent, and local branching schemes were proposed. And also the results show that the math heuristic outperformed the general solver and give a very high quality solution. And also we show how the multi-period setting helps get better solution and significant cost saving. Of course, within this research, we find other insights. I invite you to check on our journal in the European Journal of Operational Research, and it's entitled the single allocation hub location, the multi-period single allocation hub location routing problem. And as a perspective, of course, a math heuristic, as you can see, it is based on a mathematical model. And of course, mathematical model, it makes the things difficult when the size of instance are getting bigger. So it's worth investigating the meta-heuristic avenue of research to overcome the complexity and challenges that we can have in these kind of problems. And thank you so much for your attention. And if you have any questions, let me know. Thank you.
Thank you, Afaf. Very nice presentation and very good timing. So let's move to our next presenter, Hannah. Can you please share your screen?
Yes. 1 second. Okay. Can you see my screen?
Not yet.
Okay. Now?
Yep, we can see it now.
Okay, perfect. Then, hello everyone. My name is Hannah Bakker, and until last week, I was a PhD student of Stefan Nickel in Karlsruhe, and since last week, I'm a postdoc in his group. And the title of my presentation today is Pattern Recognition Meets Branch and Bound, Regional Branch Variable Selection for the Capacitated Facility Location Problem. And what I will show you within the next minutes is part of the work that I did as a PhD student. And I just want to use these next 10 minutes to give you an intuition of what I've been doing in my work and what I will continue to do as I start my postdoc. So the problem that I will be looking at, I'm sure all of you know the Capacitated Facility Location Problem, in short, the CFLP. I still want to go over it really quickly because I'm looking at a profit maximizing version of the problem. And just in short, the CFLP addresses the problem of selecting a set of capacitated facilities from a set of candidates I to serve the demands of a set of customers J. And there are two types of decisions to be taken. The first is a binary location decision indicating whether a facility is open or closed in the solution. Then there is a continuous allocation decision, which denotes the fraction of the demand of a customer J served by a facility I. And the objective is to maximize the total profit. And this is the contrast to the cost minimizing classical formulation of the problem. Here, we must not serve all the customer demand, but we must ensure that for no customer, we serve more than the total demand. And of course, all the allocations must adhere to the established facilities capacities. And so within those next minutes, I will look at two example instances, P1 and P2 that you can see right here. And they have both been obtained with the same random generation procedure from literature. And they both have 100 candidates and 100 customers that are randomly distributed on the unit square. And the profits are proportional to the resulting Euclidean distances, and the remaining parameters are then drawn from uniform distributions. So they are randomly generated. And then in this generator, the capacities are scaled in such a way that the ratio between the total capacity and the total demand adheres to a given constant. And this constant is the only difference between these two instances. For P1, it is 3, and for P2, it is 10. So in consequence, when you look at the optimal solution to these two problems, you see that for P1, more facilities operate that then serve fewer customers each, and for P2, fewer customers operate that then serve larger subsets of the customers. And so far, nothing new. We can easily obtain those optimal solutions with state-of-the-art commercial MIP solvers, as for example, provided by Cplex. However, when we look at the runtime of Cplex on the same computer, we see that it takes 0.2 seconds to find the optimal solution for P1, while it takes 12.2 seconds to find the optimal solution for P2. So despite both instances being of the same size, they obviously pose a very different challenge for Cplex, for that solver. And when you look at literature on the CFLP or on location problems in general, you observe that the analysis of the performance of solution algorithm is often an average case-based analysis, and one seldomly looks into why certain instances are more difficult to solve than others. And so what I want to, the idea that I followed through my thesis and that I also do in my work is that I want to understand whether there are maybe differences in the optimal solutions that make these solutions more difficult to find for different algorithms. And so let's look at these two solutions, two optimal solutions from a very specific perspective, namely by looking at the set of solutions that is derived for each of these two optimal solutions, which is defined here, and it is obtained when I remove every optimal facility from the set of candidates 1 and resolve the problem. And with that, I can know the role of individual optimal facilities by analyzing how the solution changes when they are not there. And so when you look at P1, you see that the removal of a single facility, as always indicated here in red, has a purely local effect. It is usually just replaced by one of the neighboring facilities. In contrast, when you look at P2, you see that the removal of this facility here in red also results in these two pink facilities that operated in the original optimal solution no longer operated, and that instead this entire region of customers is now served by a combination of facilities in lime green. And same here and same here. So you see that while in P1, facilities are optimal independently from each other, in P2, the optimal facilities interdepend, serving entire regions of customers optimally in combination. And there are two important observations to be made here. Firstly, the difference between these at first sight similar instances is the level to which the combinatorial element of the mixed binary formulation of the CFLP shines through. And this significantly affects the hardness of the problem. The second observation to be made is that facilities do not just depend on any other facility in the problem, but usually on other facilities that are relatively close in this visual representation. So there is an implied regionality that is a pure result of the location allocation structure. And so what I'm proposing, what I also proposed, is to derive these regions within which facilities interdepend more strongly. And I just want to give a very short intuition on how I did that. And that is, here you have a very simple instance with two visibly distinct regions, and assume you have a number of well-performing solutions to that instance, optimal and near-optimal solutions. And when you then sum the allocation matrices corresponding to these solutions, you will find that here, where they have these two visibly distinct regions, you have this block diagonal structure. And of course, here it is easy to identify because I arranged columns and rows in the particular order, but it is possible to derive such a block structure from arbitrary allocation matrices to several sets of two solutions to arbitrary instances by means of pattern recognition, in particular by means of spectral biclustering. And so now let us get back to the idea to our instance P2, which was much more difficult to solve since it had these interdependent facilities than P1, in which facilities were optimal individually. And what you see here is first the optimal solution, in which I indicated 4 of the facilities operating in orange, and then the solution that you obtain when you remove this facility 29 from the set of candidates. And you see that both the orange and the pink facilities serve the same region of customers. And now recall that in the CFLP, the only integer or binary variable is the location variable. And that this means that once you enter, or when you're in the branch and bound process and you enter a node and you have a fractional solution and you choose one of the variables to branch on, that variable will correspond to exactly one of the facilities. And what you see in this tree that is produced by Cplex is that when the node is orange, that means that the fractional variable chosen to be branched on that node corresponds to one of those orange facilities. And if it is pink, it corresponds to one of those pink facilities. And what you see is that despite those two sets of facilities serving the same region of customers, those candidates are branched on at very different levels of the search tree. However, it is intuitive that we will only be identifying that the branch and bound algorithms will only be able to identify this orange combination as the superior combination of facilities once it has branched on all the pink facilities. And you can see that often there are long or deep branches in the tree that can only be fathomed after the last one of those pink facilities has then been branched on. And so what I propose is to use a regional branch variable selection scheme, where first, or in every branch, you move from one region to another region so that you can identify the optimal combination for those facilities that interdepend earlier. And you can derive those regions already from the solution at the root node, already from this linearly relaxed solution to which we have applied certain cuts. You can apply this pattern recognition algorithm to identify those regions and then apply this regional branching scheme. And you can see here that for P2, the branch and not just the time decreases that you need to find the optimal solution, but also the size of the search tree, both the number of nodes that you explore as well as the depth of the search tree decrease significantly. And so in summary, I just want to be very quick. I presented two main ideas in this talk. First, the interdependence between the facilities operating in the optimal solutions to a CFLP instance is an indicator for the hardness of that instance. And secondly, these interdependence relationships induce an implicit separation of the facility customer space into distinct regions. And we can extract these regions by means of pattern recognition. And of course, several opportunities present themselves moving forward. Firstly, for deriving and classifying instances to generate more balanced benchmark sets of instances for algorithm selection, but also for algorithm development. And with that, I would like to thank you for your attention and thank the organizers for organizing this webinar.
Thank you, Hannah, for this lovely presentation. Can you please share your screen as well?
Hi, well, I am Paula Segura Martínez, and I am postdoc researcher at the Polytechnic University of Valencia. And today I am going to talk about two works we have done for solving the Rural Postman Problem with a fleet of drones. This is an overview of my presentation. I will start with an introduction, and I will briefly summarize two works we have done for the problem. Well, routing problems are among the most studied problems within the area of combinatorial optimization. And a generic definition of this problem can be the following. Given a vehicle or a fleet of vehicles and a set of transportation requests, to determine a route or a set of routes with minimum total cost that satisfy all these requests and meet 13 additional conditions. The growing interest in the study of these problems rely in the number of applications and number of situations they can model, such as the delivery of goods, the garbage collection, inspection of electrical infrastructures, or meeting reading, and so on. These problems are usually modeled mathematically by representing the network on a graph where each of its links represent a connection of the real network and has an associated cost representing the distance or the cost of traversing it. These problems can be naturally classified in two groups, depending on which part of the graph the service has to be performed. In routing problems, the service is located at the node of the graph, where in routing problems, the solution has to traverse a set of edges of the graph. And we are to focus on this second family of problems. An important routing problem is the Chinese postman problem, whose goal is to find a route traversing all the edges of a graph at least once. One extension of this problem that is NP-hard is the Rural Postman Problem introduced by Orlov, in which we have a subset of edges of the graph that are called required edges, and they have to be traversed in the solution. And we have also a set of non-required edges that they have not to be traversed, but may have been traversed in order to complete. So we are going to study an extension of this problem that considers a fleet of drones to perform the service. Drones are unmanned aerial vehicles that can be useful to improve logistics. The use of these vehicles involves significant changes in the traditional way of modeling routing problems. Well, ground vehicles in these problems may traverse an arc or an edge of the network from one endpoint to the other one and cannot travel off the network. For example, we have a truck that has to clean a street and it has to enter the street and an endpoint and exit on the other one. But if we consider an aerial drone, they can travel directly between any 2 points of the network and not necessarily between following the links of the network. So if we consider an routing problem with drones, we have that they are continuous optimization problems with an uncountable number of feasible solutions. So in this context, we're going to define the length constraint K-drones Rural Postman Problem. We consider a set of lines on the plane, each one has an associated cost, and have a depot represented by a square, and a fleet of K-drones that has a limited autonomy. Well, the goal of this problem is to find a set of drone routes, each one starting and ending at the depot and with length none greater than L, such that they jointly traverse all the given lines completely with minimum totals. This problem is a continuous optimization problem, and our mathematical approach for solving it is as follows. We are going to approximate each curved line in the plane by a polygonal chain with a finite number of segments and solving the problem as a discrete optimization problem. In this problem, the set of non-required edges forms a complete graph, and the hidden cost, that is the cost of traveling between any pair of points, is given by the Euclidean distance. But what is the drawback of this definition? The greater the number of points we add to each polygonal chain, the closer the discrete problem is to the continuous one. But if we add a great number of points, the instances becomes very hard to solve exactly. So we propose to generate smaller discrete instances by approximating each line with very few segments, but provided that the intermediate points are significant points. So our approach, we have proposed a heuristic algorithm for solving the problem and also an exact algorithm for approximating the continuous one. I am going to briefly describe both algorithms. Well, we have our continuous problem, and we are going to consider several discrete instances to approximate the continuum. So our heuristic algorithm has 3 parts. The first part, we are focused on solving the smaller instance that approximate our continuous problem. That is this instance in which we only consider that a drone can enter and exit a line and the extremes of the lines. So in the first step, we find an optimal tour, and then we split them into feasible routes and apply several local search and route optimization phases to improve the solution. We repeat this part several times, and we get an initial set of feasible solutions. And for each of these solutions, we apply the second part. To each line of the solution, we add one intermediate point in the middle, and we allow the drones to enter and exit the lines at these points. So we apply again the local search and optimization route procedures, and maybe the solution can be improved. In this picture, we can see an example of how allowing drones to enter and the middle of the lines can improve the heading cost from 1,800 to 1,600, more or less. We can see here some intermediate points that are used in the routes in this solution. The third part is focused on improve these solutions, but in spite of adding all the intermediate points, again, we select only some promising locations for the drone to enter the lines. So we are going to choose on these edges that are incident in the solution with non-required edges, we are going to add new intermediate points. And those intermediate points that are not used in the solution are going to be removed. And again, we are going to play the local search and optimization procedures. And repeating this procedure again, we add new intermediate points, we remove the unused ones, and again, apply local search. Well, we have proposed an exact algorithm for solving the discrete instances. We have formulated the problem with these two binary variables, a variable x that takes value 1 if x e is traversed by drone k, and a variable y only for the non-required edges that takes value 1 if this edge is traversed twice by me. So the goal is to minimize the total cost of the route, the total cost of the required edges, and the total cost of the non-required edges. Subject to each drone must enter and leave a vertex an even number of times. These inequalities guarantees the connectivity of the routes. Each route must not exceed the maximum length L. Each required edge must to be traversed at least once. And the second traverse for us, non-required edge must be done if a previous traverse has been done. And finally, the binary condition of the variables. Based on this formulation, we have implemented a branch and cut algorithm that incorporates separation procedures for the connectivity inequalities of the formulation at this and these 4 families of valid inequalities that we have proved that are faced inducing inequalities for the model. And we have proposed an iterative algorithm based on this formulation that is a refinement of the Mark-Heuristic algorithm we have presented, but at each iteration, we include some internal points, but in spite of use in the local search and procedures, we use the branch and cut algorithm. And we repeat this methodology until 2 hours of computational time are reached, or the algorithm reaches 5 iterations. And finally, some summarized computational results. We have tested these methods in some instances from the literature in 45 drone instances, and we have run several times the instances with different values for the parameter L in order to obtain solutions ranking from 2 to 6 drones. So a total of 225 instances are solved. This table summarizes the improvement of the second algorithm over the Mark-Heuristic algorithm. In the total of the instances, approximately the half are improved with the new algorithm over the previous one. However, we have here the heuristic needs to find the final solution, and the time the new iterative algorithm, the computing time for the iterative algorithm, and the average number of iterations this algorithm uses. Here we have a solution, a final solution of the instance with the 6 drones. We have several lines that are shared by several drones and several internal points that are used in the solution. And that's all. This work has been published in these 2 works in collaboration with Professor James Campbell and Professors Ángel Corberán, Isaac Plana, and José María Sanchís, that were my thesis supervisors. And that's all. Thanks for your attention.
Thank you, Paula, for this great presentation. Now we can leave the stage for our subject matter expert, Professor Alev, and for her comments, questions, and suggestions to the presenters.
Hello, everybody. Thanks for inviting me to this seminar and for the Eurowisdom. And also, I think that this Young Women for OR is a great initiative. It's brilliant. Thanks for organizing it. And I really enjoyed listening all the talks here today by Afaf, Anna, Paula. They were inspiring, and congratulations on your hard work. So let me start with a brief cap of what I have listened. I started with listening location and routing problem in terms of hub location and routing, and then moved to a only location problem with a classical capacitated facility location problem, and then moved to arc routing. So we spanned all the areas, the different areas in the talks. And so if you don't mind, let me start with the order of the talks and start with Afaf. So I also work on hub location problems, so I know what you have been doing in this work. It's a very good motivation. I liked your maps with problem definition. Can you give, for example, practical examples from real life? I think that this is like a supply chain network design, but it might increase the value and the impact of your work if you can relate it to more practical implementations. What type of a hub network that we might build in multi-periods? What do we mean by multi-periods? Is it a year? Is it a couple of months? And what are the routes? Are these the routes of, for example, trucks? And so that kind of a practical insight might help. Do you want to add anything on that?
Hello, thank you so much for your insights. Yeah, actually, we thought about this actually because in the work also we used different objective function, and this specific objective function that we present the last results on it, it has this kind of network that we may have the hubs are dispersed for example in a country, and then we have a long routes, and we was thinking what kind of application we would like use in this kind of hub location network. And indeed it may be, for example, for the I don't know, postal deliveries or something like that, which we can use like long routes over the multiple cities and so on. And yeah, it may be also on maritime transportation as well. And of course, whenever we choose a different objective function, we may have a very different network design. So because for example, we are using specifically the arc. We are embedding or establishing the hub arc. And what that means that, for example, we are assuming that we are investing in between hubs network. That means that, for example, it may be train or plane or so on. And we don't assume that we have capacities on the arcs, as well as for the routing. So that's why we can find this kind of network design. But if we, for example, we have capacities, or we assume that we have the capacities on the arcs, it may be different. It may be we will have a very close hubs and then very small routes or something like that. So yeah, it depends also on the objective function. Yeah, thank you so much for your insights.
Thank you for your work. And I was also thinking about, so you're proposing a meta heuristic for a difficult problem. It incorporates both location and routing, and which are both, as you mentioned, difficult problems. So what are your test instances? Another feedback that I want to give it, perhaps you would want to test your algorithm on different types of instances, benchmark instances perhaps from the literature, and then show that your algorithm works on both, well on both types of instances, because one instance set might not be enough. It might be biased through your approach. So that's another feedback I thought might be useful for you moving forward.
Thank you so much for the answer of the data that we used. We used the AP data set. Okay. But yes,
I thought you were showing a map of France. I thought you came up with a new data.
No, AP data set. Thank you.
Okay, thanks for the clarification. Okay, now I can move on to the second talk by Hannah. Thanks again, and congratulations on defending your thesis. I didn't know that you defended your thesis recently. So I really like that you looked at the solutions of the models that we built. Sometimes we see in papers that everybody talks about their CPU times, but they don't give us any insights about the results. It's just everything boils down to how fast they can solve it, but that's not we are in it for. Usually what we're in it for the solution itself. And I like that you're looking into these different locations under different parameter values and how you can drive insights from the solutions to solving the problem. And it incorporates many things. It somehow incorporates a little bit of learning and clustering perhaps, and try to incorporate it is difficult. So one thing that came into my mind is what type of problems that you can incorporate this type of insights into, not just the capacitated facility location, but moving forward in the short term, which problems do you think that you can incorporate this reasoning methodology?
Yeah, I think general location problems that have a location allocation structure at the core, because the algorithm takes only the allocation matrix as an input. So it does not consider any of the parameters of the problem. So first of all, of course, also more complex versions of these problems that take more effort per node, for example, with a nonlinear objective. So one would even benefit more from reducing the number of nodes to be explored, because one could still reorder the nodes differently. And then, of course, like covering problems or median problems that also have this location allocation structure. This is what we were thinking of doing next. Yeah.
Yeah, I see that it's easily extendable to that type of problems. It would be nice to see how it performs on those type of problems as well, and if you can implement it as a comparison. In terms of the profit maximizing setting of the capacitated facility location problem, one thing that came into my mind is usually you give a choice of not serving some customers, and we don't have the penalty of not serving them. But in every solution, we have a different set of customers that are not being served. So that's also interesting to look at, maybe. Mm-hmm. So that might, in terms of the decision maker, that's a big decision that you give which customers that you choose not to serve.
Yeah.
So this is also, I thought, might be an insight for you moving forward in that direction.
Yeah, definitely. That's something we haven't looked at yet.
Okay. Let me move on to Paula's presentation about the rural postman problem. And arc routing are difficult problems, and you're solving a difficult problems within a new setting of drones. So what I wonder, is there an immediate application of implementing these rural postman problems with drones? What do drones do?
They, for example, an application in the real world, you mean?
Yeah, real world application.
Yeah, for example, to make inspection of streets on overrated streets or infrastructures where the human operations are difficult to manage. So they can be very useful in these settings. And if, for example, for drones, if we want to make the inspection of a street, only of a part of the street, the drone may not traverse all the street, only the part that we need. So studying this type of splitting the edges may be useful for this type of applications.
I was wondering if they have started doing it. This is also valuable for humanitarian logistics applications to see, for example, after a disaster. I know that some people work with drones in humanitarian logistics. That's when after a disaster, when you cannot reach some place, drones can also do that. I just saw that Paula said that they'll just launch food delivery by drones in Dublin. That's exciting. We don't have drones using food delivery, but I see that these drone applications are getting a lot of attention in logistics, and we are moving to that future soon, I believe. Yeah, I see it's already started in some place. So I was also wondering about the problem setting. So when I looked at the formulation, the only thing that is related directly to the drones is the L constraint, length constraint, is it?
Mhm.
Okay, so I mean, it doesn't have to be necessarily a drone application then, when you look at from the modeling perspective. But then it flies to the starting point, and that's with the Euclidean distance. That's the starting depot.
Yeah,
Right?
they start. We assume that they start at the depot and constant speed, and we are not studying the technical characteristics of this type of vehicles. Mm.
Yeah, there are some, as I know in the literature, some people are looking into specifications of drones and in terms of capacity and their capability. There are technical issues related to drones as well.
Yeah,
Don't have to
especially
include them.
in those problems focused on servicing at the nodes and delivering to customers, we have to take into account the capacity and the weight of the vehicle and the weight of the package you have to transport to the customers. But for taking pictures over an infrastructures, it's not.
Yeah, and
So
I also thought it can be hidden in the edge information as well, in terms of if there's a constraint that they cannot traverse that edge, it's in the length of the edge, or it can be within the parameter that is called length, whatever there is. An immediate extension that I thought of your setting may be to consider a multi-depot setting, where you also decide on where the drones will be leaving from which location.
Yeah, we have studied some variant of this problem. We have addressing a variant that combines the delivery of packets to a discrete set of customers, a general routing problem version with drones, basically. And moreover, a variant of a multi-depot general routing problem with drones. We have also been studied these years. Mm-hmm.
Okay, so you have a clear direction for your PhD. That's good. Lots of problems to work on. Lots of difficult problems to work on.
Yeah.
So that's it from my side in terms of my feedback to the speakers. And thanks again.
Thank you so much for your comments and questions. I think it was very informative and insightful for the presenters as well. Now, thank you again, everyone, for their presentations. Now, before I close, yeah, let's take a picture together. Let's do that too. But I also want to share my screen one more time. Oops, where did it go? Okay. Okay, like I said, before we finish off, I want to just mention our upcoming events in 2024. Our next webinar is going to be in May 17th at 3 p.m. Central European Time. And our subject matter expert is going to be Corelia Curtis from University of Oxford. Then we have our events at the Euro conference this year. We're going to have our workshop the day before the conference starts on Sunday. And we will also be presenting the statuettes for the awardees for this year and last year. Here you can see a very nice picture from Euro conference in 2022, where the awardees received their statuettes. And the Young Women for OR awardees from the last 2 years, I think 17 of them is going to be attending Euro, and they're going to give presentations in addition to their regular research presentations. So if you're coming to the Euro conference, please come to our sessions as well. And then the next 2 webinars are planned for September and November for the, again, Young Women for OR webinars. And finally, as it's a tradition now, we are going to have our winter event in December to close the year. So I'd like to thank everyone again for coming and listening and sharing their work. Let me just